Okay, hello everyone. It is my absolute pleasure to introduce Professor Jens Kober, who will give a talk on robot learning through interactions. Jens Kober is an associate professor at the TU Delft in the Netherlands. He did his PhD at the TU Darmstadt and the Max Planck Institute in the lab of Jan Peters. He also did a postdoc at the Honda Research Institute and the University of Bielefeld. In 2015, Jens Kober became assistant professor at the TU Delft, and since 2019, he is associate professor at the TU Delft. Jens Kober received many awards over his career, including the George Wells PhD Award for the best PhD thesis in robotics in Europe, the Early Career Award from the Robotics and Automation Society, and even an ERC starting grant from the European Research Council. Jens Kober is really one of the foremost experts on reinforcement learning in robotics, and he's well known for his work on motor skill learning and applying reinforcement learning to real-world tasks. So I'm therefore really honored that he accepted our invitation, and here he is, Jens Kober.
Wow, thanks a lot for the very kind introduction and the invitation. Actually, so what I put together is not so much about reinforcement learning. There's a bit of that in there, but the main part I'd say is really about learning through interactions, which is the topic of my ERC starting grant. Okay, good. I also put in kind of a break somewhere in the middle after. So there are two parts, robots learning interactions and robots learning through interactions. And in between, if you like, you can already discuss the first part of the presentation. Okay, so let me start with two questions. So if you ask who should help whom, should a robot help us humans, or should a robot or should we humans help robots, then typically in robotics research, the answer is going to be robots should help us and take care of the three Ds. However, quite often in practice, actually also we need to help the robots. Kind of a similar question, which is even closer to what I'm going to talk about, is who should teach whom? And yeah, there have been since ages the ideas of, okay, we could maybe also use robots to help us teach children or teach people that are doing jobs, or more practically speaking, what we already see today is rehabilitation. But then we also have the other side that we are teaching the robots, and that's the part I'm going to focus on. So what I'm going to talk about is indeed learning motor skills, and for doing that, there are two different but complementary ways, which are also inspired by how humans teach and learn. The first one is imitation learning, which is a form of supervised learning, where the idea is that a teacher demonstrates a skill and then a student, so a robot in this case, tries to mimic that. And then the second one, indeed, is going to be reinforcement learning, where also our robots need to practice. What makes tasks hard? So what I'm talking about in terms of motor skills and tasks, that's movements that are maybe on the order of a few seconds to a few minutes. And if you want to apply that in the real world, then you get complex dynamics of the robot interacting with the environment, or maybe even the dynamics of the robot itself. And then you have all the uncertainties and variations in the objects the robot is interacting with, in the environment the robot is acting in, but then also the tasks. And it gets even worse if we consider humans with which the robot might need to interact. And the good news in terms of research topics is that it occurs in all robot domains, and the bad news as well, because that still means we are quite far from getting our robots out of these very traditional industrial settings where everything is very well defined and clearly separated. So thinking of agriculture and food production, where you have objects that are never the same, and also the environment changes frequently, household and care environments, and so forth. So that's really about learning interactions, and that's going to be the first part of my talk. And then the second question is how to learn. I mean, I very briefly talked about imitation learning and reinforcement learning already. Then if you take a look at how humans actually teach and learn, you'll notice that there's some kind of a continued interaction between the student and the teacher. While for very traditional imitation learning, you would say, okay, let's give the robot a bunch of demonstrations, give the data to the robot, and then it's off on its own to try to imitate and generalize that. And roughly the same for reinforcement learning. You'd initially define a reward function, an optimization criterion, and then the robot again is off on its own. However, what about actually including additional demonstrations while the robot is learning? How about some form of intermittent feedback, like you see in these two human examples on the right? And it's slowly picking up, but I think still that's largely missing in robot learning. And hopefully by the end of the talk, I'll have convinced you at least a little bit that there's some benefits to that in order to speed up the learning process, which enables the robots to learn more complex tasks, and which is also hopefully somewhat intuitive for humans in order to enable them to teach robots new tasks. So that's going to be the second part of the talk on learning through interactions. Okay, learning interactions. So just to give a little bit of a setting on imitation learning and where the difficulties come from is, okay, we give two demonstrations. And then we want to be able to not only reproduce exactly that, but also to be able to pick up a glass of orange juice or whatever at a new location. However, what happens then if we now start to remove the orange juice from this red coaster? Then you suddenly have to have 3 reference frames, for instance, you need to care about. So move relative to the glass, relative to the table, or relative to the coaster. And that very soon becomes combinational, in terms of combinations, becomes very expensive. And you would actually need to provide a whole lot of demonstrations. So there very soon happen to appear ambiguities on when the demonstrations don't contain sufficient information on what to do. And something similar happens if you additionally include different control modalities. So there's a duality between force and position. So if you apply a certain force to a deformable object, and that's going to result in a displacement, and the other way around. But if you want to make the robot execute something, then you actually need to decide on whether to use force control or position control. If you have exactly the same object, so this kind of a sponge always, then it doesn't really matter because they're equivalent. There might be some issues with how noisy it gets, but in principle that works. However, now if you want to generalize that and apply it to a new scenario, so maybe a sponge that has a different stiffness, then suddenly that question becomes important. So here's a little toy example on that. We were trying to flip up this box. So you could think of it as having a box in a drawer, then you flip it up so you can grab it from the short side, for instance. So that's the demonstrations with a bunch of different initial positions. And now we want to actually decompose that. So we have the kinesthetic demonstrations. It's probably way too small to see, but the different lines are multiple demonstrations. Then we have here, that's the positions and the forces, and the 2 other axes are, for instance, in world coordinates and relative to the object. And we want to process that. And actually what we want to get out is a sequence of movement primitives, so simple elementary movements that describe one part of the task. So for instance, moving towards the box would be one primitive. And then the biggest question here was, okay, so did we actually use the world coordinates or the object coordinates? Was it controlled in position mode or in force mode? And then in which dimension additionally? So what would come out of that, for instance, is, okay, initially for moving towards the box, obviously that should be in object coordinates, so we can generalize to different positions of the box. And if you're in the air, then force control doesn't make any sense. If you always want to pull it to the same position, then in order to ensure contact, you would need to apply a force in the downward direction and act in both coordinates and so forth. So how do we actually get that? We use some very simple segmentation approach that doesn't really matter, but the main idea here for determining which reference frame and which control modality is used was the idea of taking a look at whether the demonstrations are converging or diverging in the various reference frames. So for instance, here, if you take a look at the first part, so I hope you can see my mouse. If you're talking about moving towards the object, because the object can be at different locations in the world on the table, it's going to diverge for that. However, if you look at that in object coordinates, then we're always going to go towards the center of the object. So that means if you have a converging behavior, that's more likely to be the correct description. If it's constant, that's a bit less likely. And if it's diverging, then it's probably not the correct one. So we calculate some kind of a score for that, and based on that, we decide on which combination of control modes and reference frames to use. So you can see that here, where it nicely generalizes to different positions of the box. You can also move the support here, and it even generalizes to different shapes of the box. So that's one example on where we actually assumed that we have sufficient demonstrations to collect that, but then still even just finding the correct representation in this data is non-trivial. Here's a second example on unscrewing a light bulb. Here the focus was more on figuring out the correct sequence of doing things. So here, again, a bunch of demonstrations. The light bulb might be screwed in more or less. And to keep contact with the light bulb, we're actually pulling up slightly. So then in the end, you move it to the trash bin. So, okay, let me skip forward a little bit. So what we have here is we have some predefined primitives. So moving towards the bulb, grabbing it, rotating it, releasing, and so forth. And the question was, okay, what's the correct sequence? And we want to get that from the data as well as the target positions. So then from the demonstrations, you can extract something like that, where we have here a loop of repeating the unscrewing movement. And then with, I think around 10 demonstrations, the robot can reproduce that. And what we also learned is when we actually need to switch from one primitive to the next. If you can imagine, okay, we're pulling on the light bulb, and if it becomes loose and we keep pulling, then it's just going to go flying off. So we really need to detect when to stop and switch to the next movement. So that should happen in a second now. Good. So that's a few examples of imitation learning, learning from demonstration, where we assume that we give all the required data in the beginning. To be honest, in practice, that didn't work out that well. And we trained our system and then tried to reproduce it on the robots. It worked kind of, but then we discovered that we had forgotten to demonstrate something. So we went back, collected a bit more data. So effectively, it already was a loop. So now to switch gears a little bit, I'm going to talk about reinforcement learning. I just heard that you had a bunch of talks on that the last week, so I can go quickly on that, I guess. So you have states. So for instance, the robot joins the actions, torques, for instance, and every time step you apply that, you get to a different state, and you also get a reward signal, and you can roll that out. Here I'm going to focus mainly on episodic tasks, so they end at a certain time horizon, capital T. And then what we actually want to learn is the policy that maps from states to actions. And the objective is to maximize the expected return. So in the simplest case, the the cumulative rewards. And then no matter what you do, unless you go very old school and tabular, you'll actually parameterize the policy. If you have a movement primitive, that's just some low dimensional parameters. Or then if you go deep reinforcement learning, that would be the parameters in your neural network. So here is a very old example, and I'm going to tell you why I show that a bit later on. So here we actually combine an initial demonstration with reinforcement learning. The reward is something related to the distance between the ball and the cup. What you saw here is that just playing it back, you had a bit of an error after 15 trials. It's already considerably closer. Now it's going to try something different, going a bit too far. And then from 45 trials onward or so, it hits the rim of the cup and sometimes goes in. And after 100 trials or so, has really nicely converged. And back then we were really proud of that. And if you compare it to deep reinforcement learning, that's still amazingly efficient even nowadays. Okay, so let's move to something slightly different. Indeed, deep reinforcement learning. So reinforcement learning is the idea of learning behaviors using trial and error and a scalar reward function. But then if you have a real robot, then the observations suddenly become very high dimensional. So this KUKA U-bot, you have whatever the VLAN encoders and joint encoders, you have a camera there and some laser rangefinder. And in order to make reinforcement learning work, how you would structure your neural network is typically that you have some kind of a bottleneck layer that brings it down to a manageable size. And now the question is, can we do that a bit smarter rather than having the reinforcement learning on its own while it's interacting, try to figure out a good representation? Can we include some priors, some prior knowledge in order to make that representation we get here more suitable? So what would be the idea? Like I said, include prior knowledge about the world by effectively including additional auxiliary costs on for this part of the network. And then the idea would be that you hopefully will get a more general representation that then also is not extremely specific to the setting the robot is acting in. So what are typical criteria for this kind of state representation learning? Autoencoding, which is the typical encoding, decoding structure that you want to be able to reconstruct the high dimensional observations from this low dimensional latent representation. Something that is a bit more specific to reinforcement learning is that you want to be able to predict the reward, because that's in the end what you care about from this low dimensional representation. If you're talking about robotics in particular, then the dynamics or the inverse dynamics of the system should be something that is captured by this representation. And a few more like slowness and diversity. So slowness in the sense that if you only change the observations a little bit, then also the low dimensional representation should change a little bit, which happens because you get sequential observations that typically only change very little between one time step to the next. And diversity in the sense that you want to make use of the full representational power of the vector you have. And then what actually turned out is that reinforcement learning itself is the best prior, because that really forces this low dimensional representation to fit with the policy and the rewards it needs to learn. So that would look something like that in a network structure schematically. So you have the different types of observations, you somehow combine them, you want to have one low dimensional representation, and then you have, for instance, the classical deep reinforcement learning part, so a Q function in this example, and then additional criteria related to the state representation learning costs. So what you're going to see next is an experiment where we compared a few things. So using reinforcement learning only, doing the state representation learning and the reinforcement learning simultaneously, and then alternating between the two of them. So the experiment is on this Torx driving simulator, where optionally we pre-trained the lower dimensional representation on one test track, and then we had a number of different training and testing tracks. So with pre-training, so where we pre-trained the representation with one track, you see something like that, is in the training domain, it doesn't really make much difference. So training domain in this plot means we trained it on one track and we tested it on exactly the same track. So that doesn't seem to make much of a difference. However, where we really get a difference is if we train it on one track and then we test it on a previously unseen track. So that's what I mean here by test domain. And there you can very clearly see that just doing reinforcement learning without the additional criteria totally overfits to the one specific track. So I don't know, if you see you have a tree on the right and you always need to turn on the right for that corner, then that would be a very good representation for this particular track, but it's not going to generalize to a new track. There you would want to focus more on, I don't know, the boundaries of the road or something like that. And that's what you see here in the test domain, and even more drastically if we don't pre-train. That's learning both of those criteria simultaneously already works quite a bit better. And if you alternate, it works even better. The idea behind alternating is that actually some of the criteria are somewhat contradictory. So freezing the state representation and updating the reinforcement learning part, and then doing it the other way around and iterating between that helps it to get a bit more in a certain direction and stabilizes the whole thing. So that's not really interesting. If we train it on the same track as we tested on, then it does roughly the same, like we saw in the plots before. Where it gets interesting is if we train it on one track and test it on a completely different one. And then very quickly, reinforcement learning only is going to go crashing. Now, one more idea on that is, okay, now we already started alternating between training it for state representations and the reinforcement learning. Can we even split that further? So not only doing it iteratively, but really doing that in a sequential way. So the idea we had here is to use in the first phase a deep reinforcement learning approach with a value function in there for the whole network and get that to a certain level. And then in the second phase, we actually are reasonably sure that this mapping from the observations to the states already captures what we're interested in. So we could potentially freeze that and then use a different approach. So in this case, a more generic optimization approach only on the last part of the network, that is mapping from this latent state representation to the actions. Okay, and that's what you see here. Yet another simulator is here. The different lines are switching from the DQN to the optimization only of the small part that is mapping from the states to the actions at 2,500 samples or 10,000 no episodes, sorry. And yeah, so maximum you have is the stashed line. DQN reaches roughly that level and doesn't improve any further after that. By actually implementing this two-phase approach, we can get significantly better performance on this task. And well, it's a year and a half ago, I guess now. Back then, we actually got the best performance we could find on this little racing simulator in the literature by using this idea of first learning everything and then really focusing only on learning the actions. As I said in my introduction, it gets even more involved if we talk about interactions with a human. So that's a little bit unrelated, but I just wanted to show the video here. So the learning here is on the ergonomics and of the human. So which hand pose will result in what kind of an ergonomic score. So you can see the ergonomic score up here. And on the left is a planner that takes the ergonomics into account, so as an additional cost. And here, for instance, it's really put the object higher because the hand poses of the human you need for that position of the box is just a lot more ergonomic than having it down here. So can include that, for instance, in the human-robot collaboration. But in general, if you need to take into account how noisy humans are and how unpredictable, and that they always need to be safe, that just adds a whole level of complexity. And then one last video before I stop. That's recent work of one of my master students and a colleague of mine and a PhD student on actually using ontologies and reasoning and planning in a retail environment. We have a big project with a Dutch supermarket chain on that. So here it's trying to restock a shelf with these milk cartons. And then the robot is looking from here. So that's the view of the robot. So if you look yourself, you can see that there's a milk carton hidden here, but at least in the world model, it's not seeing that. So it doesn't know that there's something here. So what it's going to do next is try to push them back. It's going to observe, okay, not moving, and then reason about, okay, there needs to be an object there. So I'm done with that row. And then it's going to start on the next one. And the next step we're going to take in that direction is actually also including learning in the mix and not only relying on knowledge we have put in manually and reason about that. Okay. Questions so far? I'll try to also open the chat. So if you want to ask there, that's also fine. Ha. We can't see the chat, unfortunately. Okay, now it's there. Nope. Xing, do you want to unmute or ask in the chat or?
Yeah, thank you for the first part presentation. I would like to ask a question about the first example. It's a poor flip example.
Yes.
Yeah, exactly. Yeah, here. And I had a questions about how do you switch the behaviors between different primitives. So I assume like you detect some feature value and compare with demonstrations and to try to detect some jump condition to switch the behaviors.
Exactly, yes.
Yes, and my question is more specific. So as you said at the very beginning, the uncertainties in the environment has a huge influence on the motion planning problem. And for that example, if you flip an object on the board, but in the between there's a small collision, a very small collision that might change your force signal very significantly. And I will call it unknown contact states. So because in that example, we know exactly where the contact states, how the contact state looks like. And we know intuitively how to encode the contact states as humans. But in the environment, when the environment is more complex, there are much more contact states. There are a lot of ambiguous contact states, and the robot may have a failure. So I would like to ask you how you think about it.
Yes, I fully agree. So what we did in practice is that we assumed that the desegmentation is given, and we detected the transition trigger, if you like to call it, purely based on a data-driven approach. So we know from the segmentation that the transition should occur at that time, and then you can effectively look at the data you get from the sensors just before that time, right? So I guess we got lucky in the sense that none of these kind of peaks you mentioned that happen in between happen to look very similar to the ones we're interested in.
Okay, yeah, and I had a second question about how you encoded temporal information.
Yeah.
For doing transition. I mean, what I just saw, what I just said, the example, a possible problem. Can I draw here? Can you draw my? Can you see my drawing?
Yes.
Okay, so I just want to. So, for example, here's the object you want to flip to the board, and there's a small collision, as I said.
Yes.
If we encode temporal information or a sequence of motion or whatever uncertainties, the object, even though hit the small collision, it changed a lot of force signal, as force signal is very different from demonstrations, and because we consider about the whole sequence. I would like to ask your opinion, how you think about if it might work or it's not helpful.
So what I showed you here was completely ignoring time. So all the transition decisions were purely based on, okay, we freeze a certain position or we observed a certain force pattern or something. In general, really depending on the task, including time might be necessary, and it might actually be a good thing, like you were showing there. If I understand that correctly, you could, for instance, say, okay, we need at least so and so long before we reach a target and everything before we should ignore. Yeah, so kind of what the transition learning then needs to figure out is, and that's actually also tricky, is which sensor dimensions or modalities or whatever are actually relevant for this transition or not. And if you have demonstrations that include this kind of a little bump you had, and in the training data you see that it should not have an influence, then hopefully the learning approach will figure out that it can ignore that. And we tried all different kinds of approaches. I mean, it was still a bit before deep learning, and how to include this kind of prior knowledge on what might make sense or not. I don't have a, yeah. So it unfortunately is quite a bit task and setting dependent.
Okay, I understand. Yeah, thank you.
Okay, then I'll move on. Ooh, also running a bit late. So if there are more questions about that, I'm more than happy to also discuss them at the end, also about this part. Come on. Good. So now learning through interactions. So interactive learning very quickly. This is going to look very similar to a reinforcement learning loop, but it's actually not. So it's just a state state observe and an act loop. And now what we additionally have is a teacher in the center. In most of the things, I'm going to assume that the teacher is able to observe both the states that the robot has access to and the actions that the robot is taking. And then I'm going to focus on corrections. So not providing complete demonstrations, but just corrections. So could be move a bit more to the left, move faster or something. So relative corrections rather than absolute values, which turns out to be a lot easier for people to provide. What I didn't talk about when I showed you this rolled out reinforcement learning loop before is the exploration. So the thing a robot tries out on its own in order to figure out what works better and what works worse. And in the next example, I'm going to show you what we did is that we actually modeled the human device as a form of exploration, which then allows us to incorporate that into more standard reinforcement learning approaches. And that's also why I showed you the ball in a cup example in the beginning. So that's again, ball in a cup 10 years later, roughly, now starting completely from scratch. So no initial demonstrations, but we have Carlos in there who, while the robot is doing the movement, gives corrections, in this case, via a keyboard on, okay, move more to right, move more to left, move quicker, move slower. And now we are at trial 15. And then roughly after 20 trials or so, it can already catch the ball in the cup, which is quite nice compared to the 100 we had 10 years before. And that's also roughly on the order of magnitude you as a person need to learn that for the first time. Now switching back to imitation learning, still with the idea of how to get people involved, but it actually also connects to the state representation learning I was talking about before. So a similar idea as I just talked about with the intermittent interactions and corrections. So to be able to deal with high dimensional observations, again, here we need some kind of low dimensional representation. Here, this purple bar here. And again, for neural network encoder decoder structure. So if you do that offline, you would pre-train this part and then attach the policy you want to learn by imitation learning here as a new part of a network. That works reasonably well, but then the obvious question is, why don't we do that simultaneously again to learn both the representation and the policy at the same time? In this case, it's two branches of the networks, where you can again see this as some kind of an auxiliary cost function. That's an example of that. On the left, you see the reconstruction from the latent parameter. On the right, you see the camera image of the robot, where the task is to push this little whiteboard marker off the table. You can see it very quickly learns the reconstruction. So that's really, I mean, it's sped up, but that's the real number of episodes we needed. And then now, about 20 minutes later, that's the robot operating entirely on its own without any intermittent corrections. So kind of the same thing now for Ducky Town, learning to drive on the right side of the road. Again, raw original camera image, reconstructed image. And Rodrigo, my PhD student, is now giving demonstrations. You can see a little bit via the arrow keys on the keyboard. And then let me see somewhere here. I can see that already again after 10 minutes or so. It has learned how to drive on its own. So that was purely using the images and trying to reconstruct them. However, for many tasks, we actually need to take care of the dynamics as well. And then for a neural network, yeah, make it recurrent, include some kind of an LSTM structure. So again, very similar to what I showed before, but now the reconstruction is of the observations is not for the same time step, but for the next one. And we get that one time step later. So it's also a form of kind of self-supervised, whatever you want to call it, learning. And that actually forces this latent representation with the LSTM to also learn the dynamics. So very more control-oriented tasks, the mountain car, swinging up a pendulum. In the middle, the reconstruction. And then after a few minutes, you can learn it with the interactions. And here we compared two approaches. The coach is using these corrections, while HG Dagger is providing complete demonstrations. And then we also tried that on a real pendulum swing up task. And then after, let's see, 6 minutes or so, it can already do the task. And then here you're going to see it in a better view using this camera. And if you occlude it, then you can really see that it learned to do it based on the images and not on some kind of internal representation. And here's a robot example. What's important to know is, so that's the camera, which is somewhere up here, but the only part it really sees is this white shaded part. And it's supposed to touch the oranges later. So it needs to remember where they were and keep track of the dynamics of the moving. So after 5 minutes, it's already doing quite well. And then 45 minutes or so, it has completely converged. And what the cool thing is now that if we have learned a good latent representation, we can also very quickly learn more tasks that are similar to what we had before. So now we additionally have pairs where the robot needs to avoid those and still touch the oranges. And then after 3 minutes or so, it really already learned that, because it only needs to fine tune the representation, and then actually learning the policy is only a small part of the network and pretty quick to learn. So far, that was all in joint space. However, if you have the direct actions there, I mean, it's direct, but it can get high dimensional and is sometimes rather non-intuitive. Well, if you would do it in state space or in the end effector coordinates, you need some kind of an inverse model already to be able to do the teaching. And what you're going to see here is something where we actually learned that simultaneously. So the task is to use the laser pointer attached to the robot to draw these circle, in this case, on the whiteboard. And we're trying to give corrections here in the space of the whiteboard. So really just the Cartesian coordinates on the whiteboard, and then try to learn at the same time how to do the tasks, so how to do the drawing by, again, using these corrections, and at the same time learn, in this case, an inverse kinematics model and inverse dynamics of the robot that allows us to control it. Okay. And then one last project I wanted to talk about is coming back to my introduction on having ambiguous situations, where you have now a cup on a coaster. If you only provide demonstrations on how to pick it up if it's on the coaster, and now you suddenly start to separate those two objects, it becomes unclear with respect to which one you should move. You could put in some prior knowledge, but then that again tends to be task specific. So here, a more concrete example, we already demonstrated on how to pick up the cucumber and to put it into this crate. So that works fine, even if we move the cucumber to a different position. Now where it becomes interesting is if we swapped the two crates of the apples and the cucumbers. Now the question is, should you move relative to the world coordinates and always put it down here, or which is obviously more logical, always put it in the crate with the cucumbers and the reference frame attached to that. So here the robot detected, sorry about that. So here the robot is actually reasoning about what it knows and what it doesn't know. So if it's always at the same location, the crate, it doesn't really matter if you move relative to the world coordinates or the crate coordinates, because you're going to get the same result. It only matters if something changes. And if the robot detects that the different possibilities that it has not excluded so far are contradictory, then it's going to ask for feedback from the human teacher. In this case, it was a little push in the right direction, and then it has disambiguated that situation and can move on. Here, a different example on what happens if you change the object. So now it's wider, and it's asking, in this case, which one should I do with a graphical interface. And here a task we used for a user study on figuring out how to correctly stack boxes of tea in this case. So there was a defined order, and we compared using only demonstrations with a kinesthetic teaching in this example to using this interactive approach of only asking if the robot is unsure and wants to disambiguate different choices. So that's that. And so with the new approach, we just provide one demonstration and then the rest is interactive. And here a little NASA TLX plot on kinesthetic teaching, that's the KT, and our new approach we call LIRA, learning interactively to reason about ambiguities. It's probably not statistically significant because COVID hit and we couldn't do a large user study, but on average, definitely people had felt that doing it interactively felt nicer and was a lot less demanding. So to finish up, one video clip of a movie, because I think that belongs to every good robotics task. So that's really my dream, to teaching a robot a new skill, child's play. So to sum up, we want to be able to have robots learn interesting tasks in the real world. Big problems are that many current methods really require big data, which we often don't have, and we also need to care about safety. I gave you a few ideas on how interactive learning could work, and I hope I could convince you that it's at least promising, one of the promising ways to making teaching and learning more efficient and intuitive. Yeah, and challenges, as I said in the beginning, are uncertainties and variations related to objects, tasks, and environments. Good. So that leaves about 10 minutes for questions or so.
Yeah, thank you very much.